All right, section 2.1. Now we want to look at, now that we know matrix multiplication, we want to look at linear systems as matrix multiplication. Well, and for that matter, and scalar multiplication. Okay. So, we had begun, we're looking at linear systems, so we might have something like 2x1 minus x2 plus 5x3 is equal to 7. And maybe x1 plus 3x2 minus 4x3 is equal to 9. So, we had that, and when we wanted to solve that, right, we came up with our matrix of coefficients. And so let me write out just the coefficients here. So we've got 2, -1, 5, and 1, 3, and -4. But now notice that if I say that's times the matrix x1 or vector, x2, x3, and have that equal to 7, 9 like that, now I have what I would call a matrix equation. But you see, these two representations are really saying the same thing. Okay, so let's look at that. When we do our matrix multiplication, remember, I want to look at rows here and columns there and do dot products. So I'm going to take this first row and I'll have a 2 times x1, and I'll add to that a -1 times x2, and then add to that 5 times x3. And so there I've done the first row, first column. Now I'll do second row, first column. I'll have 1 times x1 plus 3 times x2 minus, well, plus, write it this way, plus a -4 times x3. And so that's my new matrix, and we're saying that matrix is equal to this matrix. But by definition, what does it mean for this matrix on the left to be equal to that matrix on the right? Well, each of the components has to be equal, and so that means that 2x1 minus x2 plus 5x3 has to be equal to 7, and then x1 plus 3x2 minus 4x3 has to be equal to 9. And so we can represent a system of a linear system of equations as a matrix system. So here we might do something like say, okay, our matrix A is 2, -1, 5, 1, 3, -4. Don't want that equal sign there. Then we're going to have, say, our unknown vector x, and that is the vector x1, x2, x3. And then typically we use a b, and so we'll say our right-hand side b, that vector, is the vector 7, 9. And what we're trying to solve is the matrix equation AX equals B. And so we can write it, that linear system, as a single matrix equation. And so it doesn't, at this point in time, it doesn't change how we would solve it. We would still solve it the same way. We get our augmented matrix, so our 2, oops, kind of lost what we had there, 2, -1, 5, and 7, and 1, 3, 4, and 9. And we would row reduce that. So probably first I would swap row 1 and row 2 and get 1, 3, 4, 9, and 2, -1, 5, 7. Then I would take row 2 minus 2 row 1 and put that into row 2. And so I have 1, 3, 4, 9, and then 0. -1 minus 6 is -7, and or 5 minus -8, or well, 5 minus 8, sorry, is -3. And 7 minus 18 is -11. Okay, then I would multiply row 2 by -1/7. Put that back into row 2. So I have 1, 3, 4, 9, 0, 1, 3/7, and 11/7. And now I would take row 1 minus 3 row 2 and put that back into row 1. So I get 1, 0. So I have 4 minus 9/7. That's 28/7 minus 9/7. So I get 19/7. 9 is 63/7, so I have 63 minus 33, so that's 37. And the bottom is 0, 1, 3/7, and 11/7. And so now I have my solution where I let z be arbitrary, and so I have x equals 30/7 minus 19/7z, and y is equal to 11/7 minus 3/7z. See, so I solved the system the same way, but I represent it now as a matrix equation. A single matrix equation is the same thing as a linear system. Now, let me rewrite that problem again. Okay, so we had our 2 minus 1, probably making you dizzy here. So we had 2x1 minus x2 plus 5x3 is equal to, what was the first one, 7? Right, originally, yeah, 7. And then x1 plus 3x2 minus 4x3 equals 9. All right, did I get that right? Oh, no, plus 4, sorry. Plus 4. Did I do that? Yeah, for some reason I was thinking about a negative. Oh, yeah, there is a negative. Okay. So sorry, I solved the wrong problem. So what I'm going to do is go back here and make that a plus and get rid of that negative there. Why wreck a good story with facts? Okay, well, gee, I have to even go back up here. That's a plus. That's a plus. So sorry I couldn't hear you yelling through the video. So now here everything lines up and I have the same problem, okay? And so that's our solution to this problem. Sorry about the negative issue there. But now another way to view this is that when I write this matrix out this way, what am I trying to do here? Just a second. I will get that all figured out in no time. Yeah, let's see. So I'm just trying to figure out how I want to. Okay, let's do this. Okay, there we go. Yeah, and so I'm going to put a plus in there, and so you see another way to look at this is that I took 2 times I took x1 times, that's what I want to say, I took x1 times the vector 2, 1, right? So x1 is a scalar, and then I've got the vector 2, 1, plus x2 times the vector -1, 3, and plus x3 times the vector 5, 4, and that is the vector 7, 9. So now notice here I have instead of square brackets, I've used smoother parentheses. That's absolutely allowed. You can use square brackets or the smoother parentheses. Your textbook uses the square brackets. When I type up a quiz or an exam, I use square brackets. But it just, one of those things when you're writing, we tend to get a little lazier, and it's just easier to do the smooth parentheses around the vector. Okay, so another way to look at this is that I'm taking a combination, a linear combination of the columns of A, right? So the columns of A are 2, 1, -1, 3, and 5, 4. Oops, sorry about that. -1, 3. Try that again. So the columns of A are these, and you see another way to think of this equation or system of equations, this linear system, is that I'm taking a linear combination of those columns. So I'm taking some x1 times 2, 1, some x2 times -1, 3, and some x3 times 5, 4. And again, as we get more into the theory of matrices and linear algebra, this is just another powerful way to think about what we're doing, okay? So we can either think about what we're doing as doing a matrix multiplication somewhere back here, a matrix multiplication on a vector. So we're taking some vector in 3 space, x1, x2, x3, and multiplying it by this matrix that is 3 by 2, and we are transforming that vector, x1, x2, x3, into a 2-dimensional vector, 7, 9. And we're wondering, well, what was that vector, or what could that vector be that would do that? And so that's one way to view it. And then another way to view it is that we kind of think of it in these columns, and and we could rewrite this thing as x1 times the vector 2, 1, and so forth. So this is what we call a linear combination. Anytime I add, okay, so that's the combination part, and keeping it linear, I'm simply multiplying by some constants. So a linear combination of these vectors to make this vector. And I'm just asking the question, well, what is that combination? You know, how many of these vectors, the 2 1s, should I add to these vectors, the -1, 3, and so forth? And back here, one answer would be to add, what, 0 for z. Oop. Oh yeah, x1, so there's another problem. That really should be x1, x2, and this should really be x3. Not a real big deal there. What's in a name? Maybe I was going by their nicknames. But so, one possibility is, let's try that, 30 over 7. So if I take 30 over 7 times 2, 1, and then what's the other one? 11 over 7 plus 11 over 7 of -1, -1, 3, and then plus 0 times 5, 4. What do I get? Well, doing this multiplication here, I get 60 over 7 and 30 over 7. Plus a -11 over 7. And what is this? 33 over 7. And then, of course, plus 0. And so that is equal to the vector 49 over 7. When I do the addition there, and 30 and 33 is 63 over 7. And sure enough, that gives me 7, 9. And that's what we're supposed to get, right? Back here, 7, 9. And so, you see, I can take these linear combinations of my vectors of A, columns of A, column vectors, and get my solution. Okay, so that's a couple representations using these new things we have, matrix multiplication and scalar multiplication, to represent our linear systems. Okie doke, and I think that's good for our representation.